Hey guys, it's Maggie here, and me. And today we're going to talk about oxidation and reduction further, but now we're also going to think about whether a reaction will be occurring spontaneously or if you have to make it happen. Remember in the past we talked about spontaneity with respect to Gibbs free energy? And if the value was negative, it meant that the reaction was spontaneous. Well, here we're going to decide whether a reaction for redox is spontaneous or not by just looking at how active or inactive, if you will, the metal or nonmetal is. So this is just kind of a different way of looking at it for oxidation and reduction reactions. Maggie's really happy right now because this is her favorite topic. Okay, so let's get to it. So on the screen, I have two different reactions. One is copper metal, copper solid, in a solution of zinc nitrate, and the other one is zinc solid in a solution of copper nitrate. Now, it seems like super similar, but one of the reactions is going to happen naturally, and the other one is not. So, let's see what happens. We find out that the zinc in copper nitrate solution is spontaneous, while the copper in zinc nitrate solution is not spontaneous. Let's see why that's true. So in order to understand this, we need to look at table J on our reference table. It's called the activity series, and we're going to start by just looking at the metal side and completely ignoring the nonmetal side for just a minute. So basically on the metal side, the higher up you are, the more active or like the better you are at oxidizing. So I'm just going to write right on the screen, and you should write this on your reference table if you have one handy. Ox. Because the higher up you are, that means the more you want to lose electrons. And if you look on your reference table, you will see that lithium, rubidium, potassium, cesium, barium, strontium, calcium, sodium, magnesium, I'm just reading right down the list here, all of the more active ones are in group 1 or group 2. And these guys really, really, really want to lose their electrons. And the less active metals are like kind of going closer to the transition metals, and they're not as intense on losing their electrons right away. So we're going to say that the lower you go here on the activity series, the less likely you are to be oxidized. You're not nearly as in need to give up your electrons, which makes you more easily reduced. So if you're not more likely to give up your electrons, it's possible that we could also make you take electrons. Now, of course, metals don't typically like to take electrons, but we can make it happen. So, in terms of nonmetals, it is the complete opposite, which makes sense because fluorine is the most electronegative element on the periodic table, so it wants electrons the most. So the more active nonmetal would be reduced. So fluorine is most likely to be reduced and to gain electrons, which we already know, which makes the less active nonmetals more likely to be oxidized. Because if it was a battle for electrons, iodine would have to give its electrons to fluorine because fluorine wants them more, which would make iodine oxidized. So, I would write on your reference table, write as I have ox for at the top of most active metals, reduction near least active metals, and I would write reduction for most active nonmetals up here, and ox, or oxidation, near least active nonmetals. Because that's going to come in really handy for when we're answering questions. So let's get to it. So going back to our reaction that we were looking at before, we saw that the zinc reacted with copper nitrate, but the copper did not react with zinc nitrate. And if we now look at our activity series, we see that zinc is right here and copper is down here. So the zinc, which is more active of a metal, wants to be oxidized. And in this situation, once it switches places, it's losing electrons to form the ion. So whoever is in the ion form is the thing that's oxidized. So the fact that it's more active of a metal and starts off as a solid is the reason why this reaction has occurred. So metals react by losing electrons and nonmetals react by gaining electrons. Which metal is most likely to be oxidized? So again, most active metals like being oxidized, so it makes sense that the top guy is the best at it. Which metal is least likely to be oxidized? Well, that's going to be who's at the very bottom. Funny enough, gold is last. Wouldn't that be nice to get the gold award, being last? Which element is the strongest reducing agent? Now remember, whenever it says agent, it always means the opposite thing. So if it's asking for a reducing agent, it's asking for what's being oxidized, and here we said most likely to be oxidized is lithium. So lithium. Now it switches to the nonmetal side. Which nonmetal is most likely to be reduced? Well, again, we flipped it. For nonmetals, fluorine wants to gain electrons the most. So fluorine is most likely to be reduced. Which nonmetal is least likely to be reduced? That would be whoever's down the line the furthest, and that would be iodine. Which nonmetal is the best oxidizing agent? Again, whenever there's agent, it's asking for the opposite, so who's the best at being reduced, and that would be fluorine again. Okay, so to predict spontaneous reactions for metals, two criteria must be met. The first, you must have something to oxidize and something to reduce. In a reaction, one metal must be neutral, no charge, and the other an ion. The metal being oxidized, or the neutral atom, must be higher on table J than the metal ion. So this is just like the game we were playing, that if you are solid and you are higher up, then you are going to be oxidized and lose your electrons, as long as you are reacting with something that is an ion and lower down than you. If, let's say, you have lithium ion trying to react with a lead solid, that's not going to work. The solid has to be up top and the ion has to be below it in order for the reaction to occur. So in this reaction, and I'm sorry, this should be an arrow, not a box, we have aluminum solid and copper is the ion. I know copper is the ion because it's bonded to, you have a metal and a nonmetal, so it's an ionic compound. It also says that it's aqueous, which means that it is dissolved in water. So we have our solid aluminum and our copper ion. Let's check our table and see where those guys are. So here we have our solid aluminum. Aluminum's right here. And our ion is copper. So that works because the solid is up top and the ion is below it. So that reaction should happen spontaneously. And I was correct. It says the above reaction will occur because aluminum atom is listed higher than the copper +2 ion on table J. Sweet! Okay, let's see if we can figure out these ones. Will copper solid react with silver solid? Okay, remember one of the rules was that one of them had to be an ion. They're both solids, so that's not going to work. So no, they're both neutral metals. No reaction. What about barium solid with manganese ion? So if we go back, barium solid is here, manganese ion is here, the solid is above the ion, so that works. Alright, so let's go back and see, and it says yes. Aha, the solid barium is higher on the table than the ion manganese. Will sodium ion react with chromium? So I have a suspicion it won't, because sodium's a group 1 metal, so it's pretty active. And chromium, I know, is somewhere in the middle of the reference table. And so here, sodium is the ion, and chromium is the solid. This is not going to work, because the solid has to be the one on top. In this case, sodium is the ion and not a solid. So that's not going to work. They're switched roles. So we should see, no, chromium neutral or solid is not higher than sodium ion on table J. Now you might have noticed something really interesting is that if you look at the table J, the activity series, you'll see this is the metals column, and they have listed something that is not a metal, hydrogen. Hydrogen is a non-metal. While hydrogen is a non-metal, it still has a single electron in its valence orbital, so in a way it kind of looks like a metal. So that's in part why it's included on this table. So which metals will react with hydrochloric acid? Basically, if you have any metal above H2 on table J, it will react with hydrochloric acid to form hydrogen gas. So in this case, it's the same idea as before. Here you have your calcium solid and hydrogen's your ion. And if we look here, our calcium solid is right here, and our hydrogen ion would be down here. So that reaction will happen because, again, the solid is written above the ion. And we see that here you form calcium chloride and hydrogen gas, which I don't know if you remember, but during several of our lessons I attempted to and successfully did. I ignited hydrogen and it was a fun little explosion. So, whew. Hydrogen gas is my favorite. Copper, silver, and gold do not react with hydrochloric acid, which makes sense because copper, silver, and gold are all below hydrogen. So you can't have the solid under the ion. The solid has to be above the ion for the reaction to occur. Acids react with active metals above hydrogen on table J to form salts and hydrogen gas. So basically any of these guys as a solid are going to react with hydrochloric acid, and as a result of that you're going to get some salt and some fun hydrogen gas. For example, here we have zinc solid. Zinc is above hydrogen, and as long as it's a solid, here, because hydrogen is bonded to something else, and again there's the aqueous next to it, it's in ion form, so we have our solid up top and our ion below it, so they will react, and here you form your salt with your hydrogen gas. What type of reaction is this? Well, you have one thing replacing the other thing, kind of like my prom situation, so that is a single replacement reaction. Woo! Single replacement redox reaction. Okay, We'll talk about batteries in our next lesson.